All right. So let's continue with our. We have recently discussed observer design, and in your previous courses in EE 302, we had also seen pole placement algorithm, and you have used this in within the context of this course as well. So what I want to summarize right now is a generalized algorithm that you can use to design state feedback controllers when you don't have the system given specifically in controllable canonical or observable canonical form. We will not go into designing an observer, but designing an observer follows a very similar procedure. Okay, so let's say state space design, specifically pole placement controller design for non-canonical forms. Okay, and let me try to summarize what we have seen so far. Okay, we have seen that if the system was already given in controllable canonical form, if it's given in transfer function form, but you basically find the controllable canonical form, it becomes very easy to design a controller. Similarly, if it's given in observable canonical form, or if you put it into observable canonical form, then it becomes very easy to design an observer. Okay, so let me summarize that. If system is put or given in controllable canonical form, what we have is that we have trivial. What I mean by trivial is a decoupled pole placement problem, meaning that essentially each gain variable is determined by an independent equation, so that you don't need to solve a set of coupled equations. Okay, but the system may or may not be observable. Obviously, if it's not observable, we cannot design an observer for it, at least a full state observer. And even if it's observable, okay, we have basically a non-trivial observer design problem. Okay, so that is not observer design problem. So if you make the controller design problem easy by picking the controllable canonical form, then the observer design problem may not be that trivial. Okay. Similarly, if system is put or given in observable canonical form, then the converse happens, right? Basically, you have a trivial observer design, a decoupled observer design problem. But this time, the system may or may not be controllable. That means in this state space representation, if it's not controllable, you may not be able to take all the states to the desired point in the state space. even if it's controllable, we know that the solving the problem may not be trivial. Okay, so we have a non-trivial pole placement problem. Okay, so so let's say how we should proceed, or we will see how to proceed if the system is given in a state space representation, or it's given in transfer function form. We will discuss a generalized algorithm, how to design a pole placement based controller for it. Okay, so let me say that we will assume that the system is given, or let's say is not given. Okay, is not given in a canonical form. In fact, in this case, for pole placement, we are interested in having the controllable canonical form, right? Controllable canonical form. But is verified to be completely controllable. Okay. Now, so the problem is that you are given an arbitrary state space representation, but you want to design a state feedback controller for it. Okay, design a state feedback controller for the given state space representation. So that means you cannot select, you cannot now select in which state space representation you want to put the system in. Okay, it is given in a certain form, and you want to find the state feedback coefficients for that particular representation. Okay, so let's say that this is given by states are given by phi. Okay, so we have a phi plus bu. Okay, and y is given by c times phi. Okay, now we will kind of go over a number of relationships. Now let's make first a claim. A new state definition given by a non-singular linear transformation defined as a non-singular linear transformation phi equals p to the power minus 1 times x. X is another state definition. Phi is the given state definition. This is often called the similarity transformation. And you will learn a lot about these things in graduate courses EE 501 and EE 502 if you're interested. Okay. Then this transformation, by the way, this, if phi is equal to p to the power minus 1x, it's often given in this form to make sure that p is non-singular. Okay? That's why it's given in inverse form, but we can also deduce from this is that x is equal to p times phi, obviously. P has an inverse, okay? So you can always take the inverse of that matrix. Now, this linear transformation transforms the system into its controllable canonical form. Controllable canonical form. Okay. Now, this is a claim, but we haven't yet we haven't yet shown it to be true. But at this point, okay, such a P has to be found. Okay, so we haven't yet discussed how to find this particular P. Okay, so now let me make another claim, and which is related with this first claim. And in fact, while trying to prove the second claim, we will also prove the first claim. Okay. When two state space representations are connected by such a transformation, if one is completely controllable, the other is as well. Okay, and in fact this claim is also true for complete observability as well. Okay, so let me proceed with the proof of this claim. Proof. All right, so given the original system, this is verified to be completely controllable. Q being the non-singular singular controllability matrix. Okay, so it being non-singular means that the system is completely controllable and vice versa. Also this ensures that q to the power minus 1 exists. Okay. Now, let's say this system is written as phi dot equals a phi plus bu and y is equal to c times phi, and we are given this transformation of the state where phi is equal to p to the power minus 1x and we have obviously x is equal to p times phi. Also from this, we can also write that phi dot, because p is a constant matrix, we have also this relationship. Okay, so this gives us that this system equations becomes, because phi dot is equal to p to the power minus 1 x dot equals to a times p minus 1x, because phi is p minus 1x, okay, plus bu, and also we have y is equal to c p minus 1x. Okay, now let us multiply both sides by p from the left. Multiply both sides by the p matrix from the left, and what you get is that you have p minus 1 x dot is equal to p minus 1 x plus pbu. Okay, and also we have y is equal to cp minus 1, okay, times x. Now this matrix over here is the identity matrix. A matrix multiplied by its inverse gives us the identity matrix, and therefore we get a new system which has the state variable x as given in this expression, okay, plus pbu, and y is equal to cp minus 1 x. Okay, now here we basically have a new system with an a tilde matrix and a b tilde matrix and a c tilde matrix. So this is a new system, and we will assume that this is in controllable canonical form. Okay, now what happens, let's see what is the new controllability matrix. What is the new controllability matrix? Let's call this q tilde, also non-singular, because the controllable canonical form is always controllable. So q tilde is also a non-singular matrix. Let's calculate this controllability matrix. Okay, so this is composed from b tilde, a tilde, b tilde, up to a tilde to the power n minus 1, b tilde. Okay, now let us put all the definitions in terms of a, b, and c in here. So b tilde is equal to p times b. A tilde b tilde is equal to p a p minus 1 p b. You see that inside here there is an identity matrix. Okay, we continue like this, and we have a tilde to the power n minus 1. So a tilde to the power n minus 1 means you have p a p to the power minus 1, p a p minus 1, p a p minus 1. This is n minus 1 times pb. So you see that in here all the internal p minus 1 p's become identity matrices. So this whole thing, also this becomes identity matrix. So this whole thing becomes p a to the power n minus 1 B. Okay. Also, this, for example, is PA B. Okay. So this whole thing becomes essentially P times you have B, AB, a to the power n minus 1b, which is nothing but our original controllability matrix. So you have this being P times Q. So you have Q tilde is equal to P times Q. Is a relationship between the controllability matrices of the two representations. Okay? So you can see that Q tilde is also non-singular. Q is non-singular and P is non-singular here. So all the non-singularities prove, in a sense, coincide with each other. Okay? Now, what is interesting here is that this actually gives us also a relationship to obtain P. Okay? We did not know P, but now we can find P. Okay? Let me clarify that. Moreover, by the way, this, okay, so this basically, this completes the proof because we have proven that if the two systems are related by a similarity transformation and one is completely controllable, the other is as well. Moreover, we can find this transformation P that connects the two representations can be found by multiplying the above equation from the right with Q to the power minus 1. Okay, so we have Q tilde equals P times Q, and we have Q tilde Q minus 1 equals P Q Q minus 1. This becomes the identity matrix, and this gives us P being equal to Q tilde Q minus 1. So this is the similarity transformation that we are looking for. Okay. Remember, Q Q is the controllability matrix of the given representation, and Q tilde is the controllability matrix of the controllable canonical representation. Okay. Now, what are our questions now? One question. Sorry, what kind of a question is that? Let me rewrite it. Question. Given a completely controllable state space representation in an arbitrary form, how can I find the state transformation, sorry, I didn't like this. State transformation, which means the similarity transformation, to go to the controllable canonical representation. Okay, and the answer to that is that from the given state space representation, you first find the transfer function, in fact, only the denominator is required, because that's how we can find the A and B matrices. In fact, only the characteristic equation is required. Characteristic equation, or the denominator, is required. First find the transfer function, then find the canonical representation from the transfer function coefficients. Then find, therefore, Q tilde, use with Q from the given representation to find P. Okay, so that's the kind of the verbal summary of what needs to be done in order to find what the similarity transformation P is. Okay, now here is the main question, okay, related with the design problem. Okay, assume we have a pole placement design for the canonical form. Remember, this was much easier for the controllable canonical form. And let's say that this is given by u is equal to minus k tilde times x. So x is the state definition for the controllable canonical form. And from the canonical form, it's much easier to find the gain matrix K tilde, okay, with K tilde found, okay. Now the question is, what is the feedback vector, let's call this K, for the given or original representation. Remember what was our problem, right? A system is given to you in state space form, but not in the canonical form. You want to find the feedback vector for that particular system to put the poles in the desired locations, okay? Now, if you put the system somehow in the controllable canonical form and solve the problem in a decoupled form, how can you get back to the original state space system and find the vector k? Okay, so the answer is very easy actually, because we know that we have x is defined as, from the similarity transformation, it's related with phi. So if we have u is equal to minus k tilde times x, okay, but we know what x is, so that means we can just put here p times phi, okay, so that we have the new gain. Okay, let me leave the minus outside. K tilde times p times phi. Okay, so this is our k gain matrix. Okay, remember that our system was given in a state space representation with states being defined as phi. So when we put this in terms of phi, the new gain vector becomes as defined here. So we have k, the feedback coefficients for the original system can be calculated from the canonical form k by using the transformation matrix P. Okay, here remember phi are the states of the given, we sometimes call this the original state space representation, and x are the states of the canonical, of the controllable canonical state space representation. Okay. Now with all of this, I can actually define an algorithm, and I will call this the generalized pole placement algorithm, which will put all of these things into a stepwise procedure. Okay, so let's call this the generalized pole placement algorithm. Okay. Instead of trying to use the system to construct a number of coupled, possibly nonlinear system of equations, we will follow this conversion approach. Okay, so let's summarize that algorithm in terms of a number of steps. Okay, so we have the first step. Given the system phi dot equals a phi plus bu, y is equal to c phi, as the given system, plus you have desired closed loop pole locations lambda 1 to lambda n. Okay. Now the first step is to check whether this system is controllable or not, because otherwise a solution is not guaranteed. Okay. Check complete controllability. That means determinant of Q, which is equal to determinant of the augmented matrix given by B, AB up to A to the n minus 1B. This has to be different from 0. Okay? It has to be full rank. Second step is to construct the desired the desired characteristic equation, from the poles. Okay, so that means let's call this Q desired of S. This is the denominator actually of the transfer function. In fact, we will not need the full transfer function because the controllable canonical form only uses at least the part that we are interested in. B and A matrices use only the denominator coefficients. Okay, so this is S minus lambda 1 times S minus lambda n. Okay, the product of these poles. Okay, step 3, also you will expand this obviously to find the coefficients. Okay, step 3 is from the given system, find also the characteristic equation. Q of S is equal to determinant of Si minus A. Okay, and that's going to give you a polynomial. That's going to be S to the power n plus E1 S to the n minus 1 plus up to En. Step 4, so now here we basically have the denominator of the characteristic, the denominator of the transfer function. Denominator of the transfer function for the given system, right? So from these coefficients, we can construct the controllable canonical form. So AC, the controllable canonical A matrix, is given by the specific structure that we have. With the coefficients being, sorry, let me kind of so I have minus En, minus En minus 1 up to minus E1. Remember that A matrix is constructed from the denominator of the transfer function. And also the BC matrix is just, it has its own specific form. It doesn't use any coefficients. Okay. Now from this, construct the corresponding controllability matrix. Construct the corresponding controllability matrix. It only needs A and B matrices for this particular form. So we can call this QC, but in our discussion, this is Q tilde is equal to BC, AC BC, and up to AC to the power n minus 1 BC. The next step, step 5, find the similarity transformation. Find the similarity transformation matrix that transforms the system into its controllable canonical form. Okay, remember this is given by P is equal to Q tilde Q to the power minus 1. Okay, so at this point we know the Q matrix, we know the Q tilde matrix. Okay, Q matrix, remember we had calculated here to check for the controllability of the given system, and Q tilde is calculated from the canonical form that we derived. Okay, step 6. Find the KC feedback vector using the controllable canonical form. This is simple, right? Pole placements using canonical form. As before. Okay, and now the final step is to transform this feedback vector found over the canonical form to be applied to the original system. Transform the feedback gain vector, back to the original given system. That means we have K, which is Kc times P. Okay, and P was already determined from our discussion. Okay, now let me cover an example to show all of these steps for you. Let's say example. So system is given x dot equals in numerical example minus 1, 1, 1 minus 2 x plus 1, 2 u. Here I have used x because this is the usual variable that is being used when you specify the system. But in our procedure, in fact, this corresponds to the original state phi. Okay, so let's see how we can apply our procedure to this system. Okay, desired pole locations. Let's say are lambda 1 being equal to plus 1 and lambda 2 equals to minus 3. I mean, this is a strange kind of desired pole locations because that makes an unstable closed loop system, but whatever. Okay, we know that we can use this procedure to place our poles arbitrarily in the S-plane. Okay, so here is step 1 where we check for controllability. So the controllability matrix is AB for the second order system. B is given by 1 and 2. And if you multiply A and B, you will get 1 and minus 3. So determinant of Q is equal to 1 times minus 3, 1 times minus 3, minus 2 times 1. Okay, so that is equal to minus 3 minus 2 is equal to minus 5, and that is different from 0. So we know that we have a completely controllable system. Okay. Step 2, the desired pole locations, s minus 1 times s plus 3, and that gives us q of s, or rather q desired of s. Q desired of s is equal to s squared plus 2s minus 3. Okay, so that's our desired characteristic equation. Step 3, let's find the transfer function denominator. Okay, so determinant of si minus a from the given system, and that is equal to s plus 1 minus 1 minus 1 s plus 2. Okay, sorry, the determinant of this, and that's going to be equal to s plus 1 times s plus 2 minus 1. Okay, so that is equal to s squared plus 2s plus s plus 2 minus 1, s squared plus 3s plus 1 is our q of s. Okay, the characteristic equation of the given system. Now with this, I can find the controllable canonical form. This is our step 4. Controllable canonical form is with AC given by 0 and 1, and from here I have minus 1 and minus 3 from the characteristic equation coefficients. Also we have BC equals to 0 and 1 as per the definition of controllable canonical form. Now let's take a look at what's going to be the controllability matrix. So that's going to be BC, AC, BC. So BC is equal to 0 and 1. And AC, BC will give us 1 and minus 3. Okay. Obviously that's going to give us a non-singular q tilde. Okay, step 5, find the similarity transformation P. So for that we know that P is equal to q tilde q to the power minus 1. So I will need to take the inverse of q. Okay, so let me try to do it by using Gaussian elimination as an example. Q to the power minus 1 is equal to the inverse of 1, 1, 2, minus 3. Right, this is our Q matrix, 1, 1, 2, minus 3 to the power minus 1. In order to do that, I will augment this matrix, so 1, 1, 2, minus 3, by an identity matrix, 1, 0, 0, 1. And I will subject this augmented matrix to elementary row operations. So if I multiply the first row by 2, so times 2, and subtract from the second row, that's going to give me in the first row I still have the same coefficients, 1, 0, but in the second row I will have 0 and then minus 5, minus 2, and 1. So if I continue with this, I divide all the second row by minus 5, so that this second coefficient becomes 1, and then subtract it from the first row. what I'm gonna get is the identity matrix in the first part, and over here I will have 1 1 1 1 0. Okay, so if I divide this, I will have basically 2 over 5 and minus 1 over 5. So I have made an extra step to make it clearer. Sorry, here I have, because I haven't subtracted yet, I have still a 1 here. Now I am subtracting it from the top row. So here I have 0, 1, 2 over 5 and minus 1 over 5. And when I subtract from the top row, I will get 1 and 0. And over here I will get 3 over 5 and 1 over 5. Okay. So now here this matrix is q to the power minus 1. So it's the inverse that we are looking for. Okay. So this is one way of inverting large matrices, is by using Gauss-Jordan elimination. Okay. Obviously for 2 by 2 matrix or 3 by 3 matrix, you can use alternative ways of inversion, but this is also a way that can be generalized to larger matrices. Okay, so what is my q tilde q minus 1? That is equal to q tilde is 0, 1, 1, minus 3, and q to the power minus 1 is given by our inverse at the top row. Okay, 2 over 5 minus 1 over 5. And that's going to give you, if you do the multiplication, 2 over 5 minus 3 over 5 minus 1 over 5 and 4 over 5. Okay, this is a 3, by the way. It doesn't appear as a 3, so I'm going to put it in a better way. Okay. Step 6. Find Kc from the desired pole locations, and the controllable canonical form. Okay, so we have AC in the controllable canonical form, right? 0, 1, minus 1, minus 3. Basically we have minus 1. Remember, this is equal to minus 1 minus Kc1. This is equal to minus 3 minus Kc2 from the canonical form. So we have minus 1 minus Kc1 is equal to 3. This gives us directly the first gain, which is equal to minus 1 minus 3 equals minus 4. And we have minus 3 minus Kc2 equals to minus 2. And that gives us Kc2, which is equal to minus 1. Okay, so we have Kc1 and Kc2. So Kc gain vector for the canonical representation is equal to minus 4 and minus 1. But you need to remember that you cannot, this cannot be directly used. With the given system. Because it's not in the controllable canonical form. This gain vector needs to be translated or transformed back into the given state definition. So that is our last step, step 7. K for the given representation is Kc times P. Okay, so that is equal to minus 4 minus 1 and P is 2 over 5 minus 1 over 5 minus 3 over 5 and 4 over 5. And this multiplication gives us minus 1 and 0 for the gain vector. Okay, so K is equal to minus 1 and 0. Okay, which can be used to feedback back the states of in fact states that are defined by X here, states X of the given state space representation. Okay, so if we want to sketch, you know, how this should look like, remember we had X dot equals okay, I'm not gonna do that. Okay, let me just AX plus BU as given in the problem, CX. This is our original system, and if you want to generate a state feedback from here, okay, so the output goes from here, and this is our states, so we need to use the K matrix. Obviously this needs to be with a negative sign, okay, because if we are directly feeding it to the input. Okay, so that is our example. Okay, so I'm gonna break here. This almost completes our contents for this term, but let me see whether I have another example for you. We will see about that. Okay, so let me break at this point.